Hello, in this video I'm going to go through square root rules and I'm going to show you how to apply them to some expansions and factorizations. So here are the basic rules here, starting off with slide 1. I've got root a times root b equals root ab. So an example of that would be the square root of 3, and if I multiplied it by the square root of 2, that would be the square root of 3 multiplied by 2, which you would normally do in your head, to finish off with the square root of 6. That's basically all you have to do. Now, I should just point out a little bit about how the symbols work. If you've got a single thing under a square root sign, then you can just use the square root tick like that. But if you've got multiple things under the square root sign, then you need to use a bar like that. It also works for division as well, I should say. So you can see down here, if I've got the square root of a divided by the square root of b, that's equal to the square root of a over b. Okay, I think that should make enough sense. Moving on to slide 2, a natural, how do I put it? A natural result of the slide 1 rule is that if you multiply the square root of a number by the same number, effectively you'll get a times a on the inside, and the square root of a squared is just a. Okay, so again, examples will probably help. The square root of 3 multiplied by the square root of 3 will be the square root of 3 squared, or 9, and the square root of 9 is 3. So we are always going back to the start, effectively, if you multiply the square root by itself. In slide 3 there, bottom left corner, we've got n root a plus m root a equals n plus m root a. It looks more difficult than it really is. All I'm saying is that you kind of treat the square root like a bit like a variable. So if I had 2 root 3 plus 5 root 3, then that would be the same as 2 plus 5, which is 7 root 3. That's all it means. You basically can collect like terms where the like term is a root 3. Works for subtraction as well, of course. So that's basically it. Slide 4, just note it kind of is similar to variables as well, that root a plus root b cannot be simplified any further. So for example, root 2 plus root 3 is not root 5 or root 6 or anything else. It's just root 2 plus root 3, nothing more to be done. And similarly, if I had the square root of x plus y, I can't say it's not equal to root x plus root y or anything else. There's nothing else you can do to simplify it. Obviously, if it was root 2 plus 3, you could make that root 5, but that's a different matter. Okay, so there's the basic rules. Let's have a look at some examples now. Oh, sorry, simplifying series. I forgot about that. We'll do that very quickly as well. So again, easier to show by example than it is to give you the rules, but I've written them down anyway. So the step 1 is to look for perfect squares that are factors of the number under the square root sign. So the number under the square root sign is 72, and 72 is, let me see now, 4 goes into it, 6 goes into it, 36 goes into it, just to shortcut the process. 36 goes into 72 2 times, and 36 is the square root. Sorry, and 36 is a perfect square at 6 squared. So when you're looking for factors, you would go, does 1 go into it? But that's a bit pointless. Does 4 go into it? Does then you'd go to 9. Does 9 go into it? Does 16 go into it? So you're just looking at the perfect squares. Don't worry about the rest of them. Don't worry about the fact that 2 goes into 72. That's not as important as working out the perfect squares that go into 72. But 36 is the highest common factor there. That is a perfect square. So step 2 is to split the number into these 2 factors. So that means I've got square root of 72 is the square root of 36 multiplied by 2. Step 3 is to calculate the square root of the perfect square. So you need to know your square roots. Square root of 36 is 6. So we end up with basically what we're really doing. I'll put it down, not that I would normally do this in reality, but what I'm doing is I'm splitting up the square root sign. So it's root 36 times root 2. And then I'm seeing that the square root of 36 is a 6. So I've got 6 times root 2. And then step 4, smush together. So you have 6 root 2. So 6 root 2 is a simplification of root 72. And the example I have in slide 7 will show you why you would do this. So root 48 times root 75. Now, it's just a matter of going through your perfect square so you find a match. I'm going to shortcut it because I made the problem up myself, so I know what I'm looking for. So root 48, for example, is root 16 multiplied by root 3. And root 75 is root 25 multiplied by root 3. Okay, so just to be clear, 16 times 3 is 48. 25 times 3 is 75. That's how I worked that one out. Then I will follow my steps through. So up to step 3 now. I'll do step 3 and 4 together. So calculate the square root of the perfect square, then smush them together. So root 16 is 4. So I've got 4 root 3 plus, and root 25 is 5. So it's 5 root 3. So I can now add those two together like terms using that rule that I showed you on the previous page. 4 lots of root 3 plus 5 lots of root 3 is 9 root 3. So again, why this example is significant is because to start off with, I had two square roots with different numbers. And if we go back to this here, we can see that when when A and B are different, you can't add root A and root B together. Okay, so that's as simple as you can make it, like root 2 plus root 3. But what I did is because I simplified it, I ended up with the same square root, same number under the square root sign, which is root 3. And therefore, I could use this rule here to add them together. And that's why I got 9 root 3. Okay, that's my primer on square roots and surds. Now I'm going to go through these 3 examples plus a bonus example here. So we've got x minus root 3 times x plus 5 root 3. I'm just going to use the box method, but you can choose whatever method you want to. Use the beak method if you prefer. So I'll try and do it as neatly as I can. So I've got x minus root 3 here and x plus 5 root 3 here. And then I'm just going to multiply things together as usual. So x times x is x squared. X times root 3. So you can sort of treat x like as if it were a regular whole number. So if I'm going to multiply a number by the square root of 3, then I'm just going to have x lots of that number. So I'm going to have, we normally put the square root symbol first too. So I'm going to put minus root 3 x. And note that the bar does not go over the x, so the square root symbol belongs only to the 3. Okay, next one is to go x times 5 root 3. So that would be 5 root 3 x. And then the next one would be here, which is 5 root 3 times root 3. So I'll just spell this one out for you. You've got 5 root 3 times root 3, which really means 5 times root 3 times root 3. So now if I just pick on the last two, because they're all multiplications, it doesn't matter what order I multiply things in. Root 3 times root 3 is 3. So I end up with 5 times 3. Oops, wrong colour, sorry. 5 times 3, which is equal to 15. Okay, so 15 goes in there, and there's a minus there. Excuse me. So what do I end up with? So the expansion is x squared, that's from here. Now add along the diagonals. These are both x terms, and they're both root 3s. So I can literally collect like terms by going 5 root 3 minus root 3, which will give me still 4. So it's positive 4 root 3 and then x. And then I've got a minus 15 at the end. And you're done. Okay, expansion example 2 here, root 3 plus root 2 times root 3 minus root 2. And what you need to do is you need to develop your eye for seeing patterns. This is a number plus a second number and the same number minus the same second number. So we've got a difference of 2 squares. And so we've effectively got, I would do this in one step myself, but I'm going to do it in a couple just so you can see it. Root 3 squared minus root 2 squared. And we know that squaring a square root basically leaves you with the number that's under the root sign. So that's 3 minus 2, and that is equal to 1. So it might not look like it, but it is. Expansion example 3 is a perfect square. So you should be able to utilize the pattern for perfect squares to solve this. We square the first, and then we add or subtract, but it's add because this is add. We add twice the product in the middle, so 2 times 2 root 3 times x. I'd usually just do this bit in my head, but I'm just doing it so you can see it. Plus 2 root 3 is the second term, all squared. So a square here, same as that term, but squared. square here, same as that term there, but squared, and double it in the middle. Notice I put the variable last, and the bit with the surd in it, or the square root in it, in the middle, and then the 2 at the front here. Now I'll simplify that. I'll get x squared plus 2 times 2 is 4. So it's 4 root 3 x. And again, because the square root doesn't have that little bar on it, I know that only the 3 belongs to it, so the x does not belong to it. And then I've got 2 root 3 all squared. Now I'll just do it, I think, but explain as I go along. What we're going to do is, because it's 2 times root 3, the square belongs to each part of that. So it's not like a perfect square where there's an addition in the middle. There's no addition or subtraction in the middle. So it's literally just square each part. That works over multiplication and division, not addition. Okay, so 2 squared is 4. And root 3 squared, is that rule again? When we square a square root, it's just a number under the square root sign. So we're left with 3. So we end up with x squared plus 4 root 3x, 4 root 3x plus 12, and we're done. Remember, when there's no operation to be seen, it's understood to be multiplication. So 4 root 3x means 4 multiplied by root 3 multiplied by x. Bonus example here, factorize x squared minus 18. This is an example of where we can use difference of 2 squares even when we don't have a square number. It's not that useful. You may be asked a question on the exam, but it's not a great use of difference of 2 squares. So x squared minus x squared minus 18 could be written as x squared minus root 18 all squared, which means I've got x minus root 18, x plus root 18 by using the difference of 2 squares rule. So that's how you can split it up. And if you're savvy enough, you might want to pause the video and do this yourself. But if you're savvy enough, you might see that you can simplify the surds there for square root of 18. Okay, you've either paused the video or you haven't, but here we go. Root 18, I'll do it in this little dotty box here. Root 18 equals root 9 times root 2. So we're looking for a perfect square that goes into 18, and the answer is 9. And that would equal 3 for root 9, and then root 2 to smush it together. So it would be x minus 3 root 2, and x plus 3 root 2 would be the correct answer. That'll do for this video. If you've got any further questions, please don't hesitate to ask.